Good day everyone, I am Farima Pinaw and for today, I'm going to discuss the Atomic Absorption Spectroscopy or AAS. What is Atomic Absorption Spectroscopy or AAS? It is an analytical procedure for the quantitative determination of elements such as zinc, iron, copper, magnesium, and etc. through the absorption of optical radiation by free atoms in the gas phase. So the spectra of the atoms are line spectra that are specific for the absorbing elements. So in other words, AAS is used to measure concentration by detecting the absorption of electromagnetic radiation by atoms rather than molecules. So this absorption is governed by the Beer-Lambert law, where A is the absorbance of the sample, I sub 0 is the incident light intensity, and I sub 1 is the transmitted light intensity, and E is the molar absorptivity of the target analyte for the wavelength being used, and L is the path length, and C sub G is the gas phase concentration of the target analyte. So under some simplifying assumption, this equation takes the form where A is equals to Kc. K is the constant determined by calibration and C is the solution phase concentration of the analyte. This is an example of simplified schematic of AAS instrumentation. So the light source, flame or graphite furnace, monochromator, and detector are the four most important components of AA spectrophotometer. First, radiation or light source, which emits the spectrum of the analyte element. Second is the atomizer, in which the atoms of the element of interest in the sample are formed. So monochromator, for the spectral dispersion of the radiation and separation of the analytical line from other radiation. So in other words, monochromator is used for the separation of radiation. So, and lastly is the detector. So, the detector permitting measurement of radiation intensity. The typical radiation sources for AAS are hollow cathode lamps or HCLS and electrodeless discharge lamps or EDLS. So the HCl contains a quantity of the target element in the form of a hollow cylinder. So during operation, a small quantity of the target element is vaporized. And some of the gas phase atoms of the target element becomes electronically excited and emit photons with the right wavelength to be absorbed by atoms of the target element in the atomizer. So in other words, HCLS are an ideal source for determining most elements by atomic absorption. And for volatile elements, the use of EDLS is recommended. The most common sources in AAS are flame AAS and graphite furnace AAS, or also called flameless or electrothermal AAS. So, copper, iron, and zinc are often measured by AAS, where FAAS or flame AAS, whereas in GFAAS, they measure the selenium, cadmium, and lead. The graphite tubes are the most commonly used atomizers in flameless AAS or GFAAS. Tubes are made of high-purity polycrystalline electrographite and coated with pyrolytic graphite and can be heated to to a high temperature by an electrical current. So a small aliquot, usually 20 microliter, of liquid sample is placed in the tube at the ambient temperature. So the heating program specifying the temperatures and times is designed to first dry the sample, then pyrolyze, vaporize, and atomize the sample, followed by a cleaning step. So when we say pyrolyze na, it is to make the sample decompose. So GFAS has its limitation. So a common problem in GFAS is that analyte volatility depends on the molecular form of the analyte and the sample matrix. So to overcome this limitation, chemical modifiers such as palladium nitrate, magnesium nitrate, or a mixture of both are frequently added to samples, calibrators, and controls.